I am Dr. B.L. Gorsi. Today I am going to deliver a lecture on atomic term symbol. This topic is very important in chemistry, especially in spectroscopy. Here the symbol. We know about the symbols in chemistry for elements or atoms, that is as for hydrogen or for oxygen, etc. But these symbols cannot give us more information about the spectroscopy. So this term symbol gives us the information about the resultant angular momentum and the transitions, whether they are possible or not. This, by knowing the term symbol, we can determine the transitions in atomic spectra. This term symbol is very useful, and we can analyze the atomic spectra by knowing the term symbols. Atomic term symbol. Term symbols are used to represent the states and spectral transitions of atoms or molecules. They are found from coupling of angular momenta. When the state of an atom has been specified with the term symbol, the allowed transitions can be found through selection rules by considering which transition would conserve angular momentum. The expression term symbol is derived from the term series associated with the Rydberg state of atom. Energy levels and their energy levels. In the Rydberg formula, the frequency or wave number of the light emitted by a hydrogen-like atom is proportional to the difference between the two terms of a transition. The series known to early spectroscopy were designated sharp, principal, diffuse, and fundamental, and consequently the letters S, P, D, and F were used to represent the orbital angular momentum states of an atom. Now, the atomic term symbols. For many electron systems in atoms, electrons can be arranged in a large number of ways. Some of these states would be higher in energy state in an atom, and some combinations are degenerate. The concept of spin and orbital angular momentum for the individual electrons lose significance in many electron systems. The properties of the individual electrons are coupled together to produce a single resultant angular momentum for the entire multi-electron atom. The resultant momentum is described by the quantum number J. The term symbols are used to indicate both the electronic configuration and the resultant angular momentum of an atomic state. In order to determine J, two schemes are used to describe the coupling of all the angular momentum in the atom: LS or Russell-Saunders coupling and JJ coupling. The LS coupling scheme is used when spin orbital interactions are relatively small, that is Z is less than 30. The individual orbital angular momentum of the electrons coupled to produce a resultant angular momentum indicated by the quantum number L for the state. The individual electron spin moments also coupled to give a resultant spin momentum quantum number S. JJ coupling scheme is used when spin orbital interactions are large. The spin angular momentum of an individual electron couples to with its orbital momentum to give an individual J for the electron. The individual J's coupled to produce a resultant J for that atom. Now we are going to discuss the ground state term symbol. It is relatively easy to calculate the term symbol for the ground state of an atom. it corresponds with a state of maximal S and maximal L. The term symbol has the form this: L and the left upper corner is 2s plus 1 and right lower corner is j. S is the total spin quantum number and 2s plus 1 is the spin multiplicity. The maximum number of different possible states of J for a given LS combination. J is the total angular momentum quantum number. L is the total orbital number in spectroscopic notations. So J is equal to, in ground state, J is equal to LS, L plus S, L is equal to summation of Li and S is equal to summation of Si. So this is the formula for representing the ground state atomic term. Note, in the symbol L must be replaced with its alphabetical code. That is, if L is equal to 0, it is S. If L is equal to 1, it is P. L is equal to 2, it is D. And L is equal to 3 is F. L is equal to 4 is G. L is equal to 5 is equal to H. J is the vector sum of L and S. That is, J is equal to, it starts from L plus S, comma, L plus S minus 1, comma, L plus S minus 2, and at the last L minus 1. It starts with most stable electronic configuration. Full cells and subcells do not contribute to the overall angular momentum, so they are discarded. If the cells and subcells are full, then the term symbol is this 1s0. Distribute the electrons in the available orbitals following the Pauli's exclusion principle. First, fill the orbitals with highest ML value with 1 electron each and assign a maximal ms to them. That is, for each electron it is plus half. Once all orbitals in a subcell have 1 electron, add a second one following the same order, assign ms is equal to minus half to them. The overall term symbols, the ground state term symbol. The overall S is calculated by adding the ms values for each electron, that is the same as multiplying half times the number of unpaired electrons. The overall L is calculated by adding the ML values for each electron. So if there are 2 electrons in the same orbital, add twice that of orbital ML. Ground state term symbol. The overall S is calculated by adding the ms values for each electron. That is the same as multiplying 1 by 2 times the number of unpaired electrons. The overall overall L is calculated by adding the ML values for each electron. So if there are 2 electrons in the same orbital, add twice that of orbital's ML. Now calculate J, as if less than half filled, half of the subcell is occupied, take the minimum J values, that is J is equal to L minus S, modulus L minus S. If more than half filled, take the maximum value, that is J is equal to L plus S. If the subcell is half filled, then L will be 0, so J is equal to S. And as an example, in the case of fluorine, the electronic configuration is 1s2, 2s2, 2p5. Discard the full subcells and keep the 2p5 part. So there are 5 electrons to place in subcell P, that is L is equal to 1. There are 3 orbitals. The ML values of these 3 orbitals are plus 1, 0, minus 1. That can hold up to 2 into 2L plus 1, that is 6 electrons. The first 3 electrons can take ms value is equal to plus half, that is the clockwise or motion. But the Pauli's exclusion principle forces the next two have ms is equal to minus half, that is anti-clock, because they go to the already occupied orbitals. So total S will be this for clockwise direction plus half plus half plus half, for anti-clockwise direction minus half minus half. So the total is equal to 1 by 2, and spin multiplicity will be 2s plus 1, that is equal to 2. L is equal to, for 1 0 minus 1, 1 plus 0 is equal to 1, which is P in the spectroscopic notation. As fluorine 2p subcell is more than half filled, J is equal to L plus L is equal to 3 by 2. Its ground state term symbol is then this 2s plus 1 Lj, that is equal to 2p 3 by 2. Here this is the these are the 5 electrons. So 2 in plus 1 and 2 is in 0 and 1 electron is minus 1. Now we will discuss the ground state term symbol of D2 configuration. This is the electronic configuration of D2. One electron is present in plus 2 and one electron is present in plus 1, and these are the vacant orbitals. So maximum S value will be plus half is 1, then the spin multiplicity will be 3, maximum L value 2 plus 1 is equal to 3. So symbol S F is taken. Now J is equal to L plus S up to L minus L, that is there are 3 values of J, 4, 3, 2. If less than half filled, so the minimum values of J is taken, that is 2. So the term symbol of D2 configuration in ground state is 3F2. Now further details of atomic term symbol will be discussed in next part of video. If you have any doubt regarding this video, then you can comment me and I will try to clear you your doubts. Thanks.